Hello everyone, welcome to my lecture. Here we have a discussion about Cauchy sequences. Here you can see the definition of Cauchy sequences. A sequence xn in a metric space X is said to be a Cauchy sequence if given epsilon greater than 0 or for any epsilon greater than 0, there exists a positive integer m depending on that epsilon such that d of xn comma xk, that means the distance between xn and xk will be lesser than epsilon for all nk greater than or equal to m. Okay, then we can say that if this inequality is happening, then we can say that that given sequence is a Cauchy sequence. Okay, so here you can see one example. The sequence 1 by n in Rd is an example of Cauchy sequence. I will show you how. Okay, let's see how this is a Cauchy sequence. Okay, if one sequence is a Cauchy sequence, it will follow this condition. That means for any epsilon greater than 0, you can always find a positive integer m. Okay, such that d of xn xk will be lesser than epsilon for all n comma k greater than or equal to that m. That means if you take this m and beyond that m, okay, if you take any integers greater than that m, the distance between xn and xk, the values of the sequence for those n and k will be lesser than epsilon. Okay, that means the distance between points in the sequence, the distance between terms in the sequence are decreasing here. Okay, such sequences are known as Cauchy sequence. This is an example here. Sequence 1 by n in Rd. Let's see how this is a Cauchy sequence. For that, first we need what? First we need given epsilon greater than 0. Okay, suppose you have an epsilon greater than 0, an arbitrary epsilon. Okay, then we will show that for that epsilon, it is possible to find a positive integer m such that this inequality will happen. Okay, so since that epsilon is arbitrary, it is true for any epsilon greater than 0. Okay, so that means this is a Cauchy sequence. Okay, so let's begin with let epsilon greater than 0 be given. Let epsilon greater than 0 be given. Okay, let epsilon greater than 0 be given. What we need to find here? We need to find a positive integer m. Okay, we need to find a positive integer m such that for all nk greater than or equal to m, for all nk greater than or equal to m, d of xn comma xk will be lesser than epsilon. Okay, yes. So let epsilon greater than 0 be given. We need to find a positive integer m. Okay, we need to find a positive integer m. All right. Yes, such a positive integer m exists. I'm choosing that m. Choose m that is greater than 2 by epsilon. It's possible, right? Because 2 is a positive real number. Epsilon is also positive real number. So one positive real number by another positive real number, the result is always a positive real number. So by Archimedean property, you can always find a positive integer m that is greater than any real number. Okay, by Archimedean property, it's possible to find an integer greater than a real number. Okay, so 2 by epsilon is a real number, so it's possible to find an integer greater than that real number. Okay, I'm choosing my m to be greater than that 2 by epsilon. Okay, so m is greater than 2 by epsilon. So m is greater than 2 by epsilon means what? 2 by epsilon will be less than m. Okay, 2 by epsilon will be lesser than m. Okay, now just interchange the position between epsilon and m. So m take it to the denominator and epsilon you can take it to the numerator. So that means 2 by m lesser than epsilon. Okay, 2 by m lesser than epsilon. All right. Suppose this is inequality number 1. Okay, inequality number 1. Next, let's take the distance between them. Okay, the distance between points. Okay, d of xn comma xk. Okay, d of xn comma xk. Let's take that distance. So d of xn comma xk will be equal to what? This is the usual metric on real numbers, right? So what is the distance between any two points on a real number? That is the modulus of the difference between them. Okay, so this is modulus of xn minus xk. Okay, modulus of xn minus xk. That is equal to what? That is equal to modulus of xn means 1 by n minus xk means 1 by k. Okay, so 1 by n minus 1 by k. That is equal to modulus of 1 by n. 1 by n minus 1 by k can be written as 1 by n plus minus 1 by k. All right, 1 by n plus minus 1 by k. Now I'm going to use a property of modulus. We have a property of modulus. Mod a plus b is always lesser than or equal to mod a plus mod b, right? Mod a plus b is always lesser than or equal to mod a plus mod b. Let's use this. Okay, so here mod 1 by n plus 1 by minus 1 by k will be lesser than or equal to what? Mod 1 by n plus mod minus 1 by k by using this property. Okay, so lesser than or equal to mod 1 by n plus mod minus 1 by k. Okay, so that means here d of xn comma xk, d of xn comma xk lesser than or equal to this one. So mod 1 by n, 1 and n both are positive. So mod 1 by n is equal to 1 by n itself plus minus mod 1 mod minus 1 by k. Okay, so if you take this mod, you can remove this minus. So this simply becomes 1 by k. Okay, so d of x and xk, the distance between xn and xk lesser than or equal to 1 by n plus 1 by k. Suppose this is inequality number 2. Okay, suppose this is inequality number 2. Next is this. See here, we need for all n comma k greater than or equal to capital M. Okay, we have for all n comma k greater than or equal to capital M. So let's take n k greater than or equal to cap. Okay, for all n comma k greater than or equal to capital M. All right, that means n is greater than or equal to m and k is also greater than or equal to m. Okay, so we can write n greater than or equal to m and also k greater than or equal to m. They are separately greater than or equal to m. That means what? If n is greater than or equal to m, then the reciprocal of this one will be lesser than or equal to reciprocal of this one. Okay, so n is greater than or equal to m means reciprocal of n will be lesser than or equal to reciprocal of m. If you take the reciprocal, the inequality will get reversed. That means we can write 1 by n lesser than or equal to 1 by m. Same thing will happen here also. 1 by k will be lesser than or equal to, greater than or equal to becomes lesser than or equal to if you take the reciprocal. Lesser than or equal to 1 by m. All right. Now, suppose this is inequality number 1 and this is inequality number, 1 and 2 we have already taken. Suppose they are inequality number 3 and inequality number 4. Next, what will happen if you add this 3 and 4? Inequality number 3 plus inequality number 4 becomes what? In inequality number 3, left side is 1 by n. Inequality number 4, left side is 1 by k. So just add them. So 1 by n plus 1 by k. Lesser than or equal to right side, both of them are 1 by m. Okay, so 1 by m plus 1 by m. Okay, so that means 1 by n plus 1 by k lesser than or equal to 1 by m plus 1 by m becomes 2 by m. Okay, 2 by m. Suppose this is inequality number 5. Inequality number 5. Next, I'm going to combine these three inequalities. Inequality number 1, inequality number 2, and inequality number 5. Let's combine these inequalities. Combining inequality number 1, 2, and 5. What will happen if you combine them? What will happen if you combine them? See, here you have inequality number 2. Okay, let's begin with inequality number 2. Inequality number 2. So that means d of x and xk lesser than or equal to 1 by n plus 1 by k. So d of xn xk lesser than or equal to 1 by n plus 1 by k. Now to this I am going to apply inequality number 5. According to inequality number 5, we know that 1 by n plus 1 by k will be lesser than or equal to 2 by n. So this 1 by n plus 1 by k lesser than or equal to 2 by m. All right. Next, apply inequality number 1, the first inequality. According to the first inequality, we have 2 by m less than epsilon. So this 2 by m can be written as less than epsilon. At the end, what we got? This d of x and xk less than epsilon. For all what? For all n comma k greater than or equal to m. Okay? Yes. So we can write d of xn xk less than epsilon for all n k greater than or equal to m. Okay. So this completes the proof that the given sequence is a Cauchy sequence. Okay. I hope it's clear. Thanks for watching. Bye bye.